Hello, everyone. I hope you're all safe and sound. Welcome to the 14th lecture on analog and digital electronic circuits, in which we will study small signal analysis of common source and common gate amplifier configuration. So I'll begin with the discussion of common source amplifier without bypass capacitor, and I will analyze this circuit for the DC currents and voltages, its small signal parameters, and the maximum metric swing. Then I will quickly go through the common source amplifier configuration with partial and full source bypass. And after that, I will analyze common gate amplifier again for the DC voltages and currents, its small signal parameters, and the maximum metric swing. So this is the full circuit for common source amplifier without bypass capacitor, in which Vsig is the source signal to be amplified. Rsig models the internal resistance of Vsig. Cin is a coupling capacitor which blocks the DC currents and voltages and avoid the interaction of these DC currents and voltages with the source signal. Cout is another coupling capacitor which blocks the DC component of the drain current and drain voltage and prevents them from appearing at the output, and RL is the load resistance. So we will assume that Vsig is small enough that the resulting signal, small VGS, satisfies the small signal approximation. And in this context, Vsig will be called a small source signal. And since we know that under small signal approximation, the MOSFET as well as their resulting amplifier acts as a linear circuit, we will carry out the AC and DC analysis separately and then combine the results later on to get the overall output through the principle of superposition. So this is the DC equivalent circuit of the common source amplifier without bypass capacitor, which is obtained by killing the AC source, short circuiting the AC signals, and open circuiting the capacitors. So as you can see that it is a voltage divided biasing network with source degeneration resistance. And we've already analyzed this circuit before, in which we found that the gate voltage was given by this fraction of VDD. Because IG is 0, R1 and R2, they are in parallel. So VDD is divided between R1 and R2, and the voltage across R2, which is the gate voltage, is given by this fraction of VDD. So again, following the guidelines that I laid down for the analysis of DC analysis of general MOSFET circuits, we check the gate voltage, and if it is greater than the threshold voltage of the device, we assume that the transistor is in its on state, and then we find the drain current, assuming that it is in saturation mode. We find the drain current by this quadratic dependence and the drain to source voltage by applying KVL at the output too. So here, please note that I have ignored the effect of channel length modulation for simplicity. So finding this ID and VDS, we analyze VDS and we check whether it's greater than the overdrive voltage or not. Either you can check VDS for this relation, or you can check VD for this relation. VD is VDD minus IDRD. So you can find VD and check whether it is greater than VG minus V threshold. If it is, then the device is indeed in saturation mode, and ID VDS gives us the bias point of the circuit. Otherwise, we'll assume if this condition is not met, then the device is in triode mode, and we'll have to find the drain current again using the triode mode equation, which is given by this expression. And then using this ID and this VDS, we can solve these two equations for the bias point of the circuit. If the bias point is given by these two equations, then the device or the NMOS will not be in saturation. So for this circuit of common source amplifier of common source configuration to act as an amplifier, we should make sure that the bias point is given by this set of equations, these two equations, because we know that there is no application obtained from from the NMOS when it is operating in the triode. So this is the small signal AC equivalent circuit of common source amplifier, and we are assuming that we are operating this circuit in the mid-band frequency range, in which the capacitive reactance of the coupling capacitors is small enough to be ignored, and the capacitive reactance of the parasitic capacitors or the internal capacitors is large enough to be ignored. So the internal capacitors have been assumed open circuit, and the coupling capacitors have been short circuited. So Ri in this circuit represents the input resistance of the amplifier, which is the resistance seen looking into the input of the amplifier between this node and ground. Similarly, R0 is the output resistance seen looking into the drain between this node and ground. And Vi is the, since this node and this ground makes up the input port, so the voltage across the input port, which is the input voltage of the amplifier, is labeled as Vi. And the current entering the input port is labeled I-sig. So I-sig is the small signal input current of the amplifier. VL is the small signal load voltage, AC component of the load voltage across the load resistor RL, and IL is the current through RL, and ID is the small signal drain current, IS is the small signal source current. So please notice that because of this resistance RS and R0, this amplifier configuration is not unilateral. Because for instance, if there is a change in VDS, then this change in VDS will change the current through R0, which will change the source current IS, which will change the voltage at the source node, which in turn will change the voltage VI, because VI is VGS plus the voltage at the source node. So any change in VDS will be reflected on the input side in VI, which is why this circuit is not unilateral. Hence, the input resistance should be computed without any constraint of open circuiting the output. However, in this case, because of the zero gate current, because of infinite resistance between gate and source, we see that the input resistance is given by the parallel combination of R1 and R2. So there is no current going into the gate side. So input resistance Ri by definition is given by Vi over I-sig. So Vi over I-sig is R1 in parallel with R2, because all of I-sig will flow through this resistance. So Ri, which is the input resistance of the amplifier of the common source amplifier, is given by this simple expression. It is just R1 in parallel with R2. That is, Ri is independent of the load resistance Rn. Output resistance of common source amplifier, however, is given by this expression. So if we go back to the AC equivalent circuit, then R0 is the resistance seen looking into the drain between this port, looking into the drain between this node and ground. So we know that the resistance looking into drain between this node and ground is RD in parallel with whatever is the resistance looking into this side of the circuit between this node and ground, by short circuiting the input of the amplifier. So output resistance is measured by short circuiting VI. So we short circuit VI, which means that we connect this node to ground. So connecting this node to ground short circuits this resistance and brings gate to AC ground. So this directly, in fact, brings gate to AC ground, because we are connecting this node to ground, and this node is the gate terminal. So output resistance is obtained, is computed by short circuiting the gate to ground, and then by computing the resistance seen looking into this side before RD, into this side between this node and ground. So R0 is then RD in parallel with this resistance, and this resistance is found by connecting a current source here between this node and ground, and by measuring its terminal voltage. So the reduced AC equivalent circuit by short circuiting the gate to ground. So this is the gate terminal. So we have short circuited the gate to ground, and this is the source terminal. And we have applied a current source at the drain before RD, and we wish to measure its terminal voltage Vs. So the ratio Vs over Is will give us the resistance seen looking into the drain before RD, and then its parallel combination with RD will give us R0. So since we have short circuited gate to ground, so gate is essentially this terminal now. So this is grounded. So the voltage of gate with respect to source is VGS. So since gate is grounded, voltage of ground with respect to source is VGS. Voltage of source with respect to ground will be minus VGS. This is essentially the gate terminal now. So voltage of source with respect to gate, which is the ground, is minus VGS. That is why I've labeled the voltage across RS as minus VGS. Furthermore, we notice that because of the infinite resistance between gate and source, it does not matter whether we short circuit VI or V6. Because even if we short circuit V6, even if I short circuit this node to ground, then I will have at this gate terminal a parallel combination of R6 and R1 in parallel with R2. But because there is no current on the gate side, there will be no current flowing through this parallel combination of R6 and R1 in parallel with R2, which means that there will be no drop across this equivalent resistance, which means that this gate terminal will be at the same potential as this ground. So gate will, even if we short circuit V6 to ground, gate will be essentially at AC ground. So the resulting equivalent circuit will be given by this diagram. So R out is equal to R naught, because it doesn't matter if we short circuit V6 to ground or VI to ground, we'll get the same equivalent reduced AC equivalent circuit given by this diagram here. So R out as well as R naught is given by RD in parallel with the resistance of this circuit. So the resistance of this circuit, which is given by the ratio of Vs to Is, because it is the resistance between this node and ground, can be found by observing that Is divides between R naught and GM-VGS and then combines again to flow through RS. So the current through RS is Is. And IS-RS is the voltage at the source, which is equal to minus VGS. So minus VGS is IS-RS. And then we can write Vs, which is the voltage of this node with respect to ground, as the sum of VDS plus the voltage at the source, which is minus VGS. So Vs is VDS minus VGS. VDS is the current through R naught, and the current through R naught is Is minus GM-VGS. So the current through R naught times R naught. So we replace minus VGS with plus IS-RS. We take Is out common and divide with Is on the other side, and Vs over Is is given by this expression. So R out as well as R naught, they are given by RD in parallel with this expression. So if we assume that small R naught is much greater than RS and RD, which is a very reasonable assumption, then this term will be much greater than RD, and hence R out as well as R naught, they are more commonly given by this approximate expression. That is R out, which is the output resistance of the source and amplifier, and R naught. They are almost equal to RD for a common source amplifier under this very reasonable assumption. So in order to find the open circuit voltage gain of common source amplifier, we'll have to remove the load resistor RL. So RL is removed and the output voltage is labeled V naught. So we wish to find V naught over VI and then V naught over V seg. So V naught is equal to minus ID times RD, because minus ID flows through RD to generate V naught. And ID in turn is the current through R naught plus GM-VGS. So like I said, V naught is minus ID RD and ID is GM-VGS plus IR naught, where IR naught is the current through R naught. So instead of finding the current through R naught for this circuit, we will find the current through R naught for the complete AC equivalent circuit in which RL is connected, because then we will use this expression multiple times later on. So analyzing this circuit, this is the complete AC equivalent circuit in which we have RL connected. So we wish to find R naught we wish to find IR naught, which is the current flowing through R naught in this circuit. So IR naught is given by VDS over R naught, and VDS is VD minus VS. VD is the voltage at the drain with respect to ground, which is equal to minus ID times RD in parallel with RL. And VS is the voltage at source with respect to ground, which is ISRS, and IS is ID. So using these expressions, we can write IR naught as VDS over R naught. Like I said, VDS is VD, which is this expression, minus VS, which is this expression. So IS is equal to ID. So we take ID out common, and then we replace ID with GM VGS plus IR naught. We take IR naught onto the other side, simplify, and this is what we get. So this is the expression for IR naught for the complete AC equivalent circuit in which we have RL connected. And this expression is in terms of VGS. So we put this expression back in here, take VGS out common, simplify, and express V naught in terms of VGS, which is given through this factor. So now we wish to find out VGS. And again, instead of finding VGS for the for this reduced circuit in which we don't have RL, just like IR naught, we will find VGS for the complete AC equivalent circuit, which is given by this diagram. So we wish to find this VGS, because once we'll find the VGS for this complete circuit, we can use VGS later on by for special cases of RL. So VGS is, so VI is VGS plus VS, which means that VGS is VI minus VS, and VS is ISRS, and IS is ID. So let's use these expressions again to find VGS. So like I said, VGS is VI minus ISRS, IS is ID, ID is as before GM VGS plus IR naught. IR naught is the current flowing through R naught, which is given by this expression for the total complete AC equivalent circuit. So we put it here, take VGS out common, simplify, take this term with VGS onto the other side, simplify, and we get VGS in terms of VI. So this is the expression for gate to source voltage, small signal gate to source voltage for the complete AC equivalent circuit in which we have RL connected. So I forgot to mention one thing, that when I put IR naught back in here to solve for V naught, I replaced RL with infinity, because V naught is computed when there is no RL. RL is infinity. So we replace RL with infinity in this expression, and the resulting expression is put back here to get this simplified expression, which is then solved to get this expression. Similarly, this is the expression for VGS of the complete AC equivalent circuit. But we want to find V naught in which RL is infinity. So we replace RL with infinity in this expression, and we put the resulting expression back in here, which is this. So there is no RL. RL has been replaced with infinity. So V naught has been expressed in terms of VI, and V naught over VI, which is the, by definition, the open circuit voltage gain of the amplifier, is then given by this expression, because this denominator gets cancelled with this numerator and will be left with this factor. The overall loaded voltage gain can be found by, again, analyzing the complete AC equivalent circuit in which we have RL connected. So now we connect RL back. We call the output voltage VL, and we see that the output voltage VL now, which is the load voltage, is given by minus ID times RD in parallel with RL. So VL is minus ID, RD in parallel with RL. ID is GM VGS plus IR naught. So we use the full expression for IR naught because we have RL connected back now. We are using the full AC equivalent circuit. And then we simplify in terms of VGS, and then we use the full expression for VGS here, and express VL in terms of VI. So VL over VI can be found to be equal to this factor. And then we multiply VL over VI with VI over V6, we get VL over V6, which is the overall voltage gain of the amplifier, loaded voltage gain. So VI over V6 is equal to this loading factor on the input side, because VI is RI times RI divided by RI plus R6 times V6. So VI over V6 is this factor. And we've already found RI to be equal to this simple parallel combination. So this is the overall voltage gain, or the loaded voltage gain of common source amplifier. So again, we can use these reasonable assumptions that small R naught is much, much greater than RS plus RD, which implies that small R naught is much, much greater than RS plus RD in parallel with RL. Because RD in parallel with RL is smaller than RD. So if small R naught is much, much greater than this combination, it is definitely much, much greater than this combination. And under the assumption that small R naught is much large, the output resistance R naught, capital R naught, is approximated by RD. So using these expressions, we can simplify AV naught. So small r naught, so this first term is small r naught plus this third term, RS plus RD. Since small r naught is much greater than RS plus RD, the sum of the first term small r naught and the third term RS plus RD is approximated by r naught. So we'll be left with this term in the denominator and this term in the numerator. R naught gets cancelled with r naught, and we'll be left with minus GMRD over 1 plus GMRS. So this is the more commonly found expression for the open circuit voltage gain of common source amplifier. Similarly, the first term in this denominator is small r naught and the third term is RS plus RD in parallel with RL. So using this assumption, this sum is approximately equal to small r naught, which approximates the denominator by this term. And then in the numerator we have small r naught and the other terms, so small r naught gets cancelled, and the overall loaded voltage gain of the amplifier is given by 1 plus GMRS in the denominator, the factor of 1 plus GMRS in the denominator, and minus GM times this parallel combination in the numerator times this loading factor. So again, this is a more commonly found expression for the loaded gain of common source amplifier. And you can open it up and see. So RD in parallel with RL is RD RL over RD plus RL. So you can combine RD with minus GM, and you can take the other factor of RL divided by RL plus RD. You can separate that factor out. So minus GM RD over 1 plus GM RS is AV naught. So this factor here is equal to AV naught times RL over RL plus RD, where RD has been replaced with R naught, capital R naught. So if you look at this expression, then this is the expression for the voltage gain, overall voltage gain of a unilateral amplifier, which is modeled by this two-port network. So this is the unilateral model of a two-port network in which V naught is equal to AV naught VI. So when we connect RL here and V sig through R sig here, then VL is AV naught times VI times RL over RL plus R naught. So AV naught times VI times RL over RL plus R naught. And VI is equal to RI over RI plus R sig times V sig. So RI over RI plus R sig times V sig is VI. So you can take V sig to the other side, and VL over V sig will be exactly given by this factor, which is equal to this approximate loaded gain of the amplifier. So the overall approximate loaded gain of the amplifier follows the unilateral model of the two-port voltage amplifier. To find the short circuit current gain of common source amplifier, we short circuit the output. That is, we replace RL with 0, and we call the current through short circuit as I subscript O comma S. So IOS is the short circuit current, and we wish to find IOS over I sig. So in this case, there will be no current flowing through RD because all of the minus ID will flow through the short circuit. So IOS will be equal to minus ID. ID in turn is GM VGS plus IR naught. Now we don't have to compute IR naught again. We have IR naught for the complete circuit. So we can find IR naught for this circuit by replacing in the expression we obtained for the complete circuit RL with 0. So we use the expression for IR naught we obtained for the complete circuit, and we replace RL with 0 to get the expression for IR naught for this circuit, because in this circuit RL is 0. So we get this reduced expression for IR naught. We put it back in here and express IOS in terms of VGS. And then we use the expression for VGS by replacing RL with 0, because we have the expression for VGS for the complete circuit. We replace in that expression RL with 0, and we'll get the expression for VGS in this circuit, because in this circuit RL is 0. So replacing RL with 0 in the expression for VGS and putting the resulting expression back in here, we get IOS in terms of VI through this factor. R naught plus RS is cancelled with R naught plus RS, so we are left with this factor. So the short circuit current gain can be found by taking the ratio of IOS to VI, and then by observing that VI is actually I sig times RI. So VI by definition is I sig times RI, and the short circuit current gain then becomes IOS over VI into VI over I sig. because this gives us IOS over ISIG. So IOS over VI is this factor, and VI over ISIG is RI. So multiplying this factor with RI gives us the short circuit current gain of the of common source amplifier. Again, we can find the loaded current gain, which is the ratio of IL to ISIG. So again, referring to the actual complete AC circuit of common source amplifier, we have RL connected. So IL, the current through RL, is actually equal to a fraction of minus ID, because minus ID divides between RD and RL. So IL is actually given by minus ID times RD over RD plus RL. That is the current division of minus ID. So IL is minus ID times RD over RD plus RL. ID is again GM VGS plus IR naught. We use the full expression for IR naught now because we are referring to the complete AC circuit now. We are finding the load current by connecting the load resistor back in. So we use the full expression for IR naught, we simplify, and then we use the full expression for VGS and simplify, and we get this term. So we relate the load current with VI through this term. VI is again ISIG times RI. So IL over VI, which is this factor, times VI over ISIG, which is RI, gives us the overall current gain. So IL over VI times VI over ISIG is IL over ISIG, which is the overall loaded current gain, which is equal to this factor times RI. Again, using these reasonable assumptions, we can approximate short circuit and loaded current gains. So small R naught can be assumed to be much greater than RS plus RD, which implies that it is much greater than RS plus RD in parallel with RL, because this factor is smaller than RD. And this also implies that small R naught is much greater than RS. So under these assumptions, when small R naught is much greater than the second term, which is RS, then small R naught plus RS is almost equal to small R naught. So we'll be left with small R naught plus GM R naught RS. So R naught will get cancelled out and we'll be left with this commonly found expression of minus GM RI over 1 plus GM RS for the short circuit current gain of the common source amplifier. Similarly, in this expression, small R naught, which is the first term, is much greater than this third term. So the sum of first term and third term is approximately equal to small R naught. So we'll be left with this term in the denominator. And in the numerator, we have minus GM R naught RI and then this factor. So R naught, small R naught will get cancelled out in the numerator and denominator, and this is the approximate and more commonly found expression for the overall loaded current gain of common source amplifier. So please note that all of the expressions derived for the loaded current gain, short circuit current gain in 23, overall loaded voltage gain and in 16, and open circuit voltage gain in 14, all of these expressions, they have negative sign in them. So this negative sign is indicative of the inverting nature of common source amplifier. So common source configuration is an inverting configuration. Maximum symmetric swing of common source amplifier can be obtained by finding maximum positive and maximum negative swing. So maximum positive swing can be obtained by analyzing the overall circuit for common source amplifier. Because of this capacitor, the drain voltage, the DC component of drain voltage is blocked, and only the AC component of drain voltage appears as VL across RL. So VL, the total load voltage, is just the AC load voltage, small v subscript small l, which is equal to the AC component of the drain voltage, small vd, because DC component is blocked by the capacitor. So as VL increases in the positive direction, the current through RL will increase. And since small VL is equal to small VD, so as small VL increases, small VD increases, which means that the drain voltage, total drain voltage, which is capital VD plus small VD, it increases. Which means that the voltage drop across RD will decrease, which in turn means that the current through RD decreases. So as VL swings in the positive direction, current through RD is decreasing, current through RL is increasing. Since the drain current is equal to the current through RD minus the current through RL, so the drain current will decrease. And VL will attain its maximum positive value when drain current becomes 0. That is when transistor enters the cutoff mode. So under this condition, we replace VL with VL maximum positive. We denote VL with VL maximum positive. So the current, the drain current, when drain current becomes zero, then the current through RD becomes equal to the current through RL. So current through RD is VDD minus the drain voltage over RD, and current through RL is VL over RL. Under this condition, VL is replaced with VL maximum positive. So VD has DC component and AC component. AC component of VD is VL, which under this condition is written as VL maximum positive. So we take the AC component to the other side, and then we realize that VDD minus VD over RD is the current flowing through RD, the DC current flowing through RD, which is the same as the drain current, because at DC, when capacitor is open circuited, the current through RD is the same as the drain current. So we replace this expression with ID, and 1 over RL plus 1 over RD when taken to the other side becomes RD in parallel with RL, because 1 over RL plus 1 over RD whole inverse is RD in parallel with RL. So VL maximum positive is given by ID times RD in parallel with RL. Similarly, as we can again analyze this circuit for negative swing of VL and find the maximum negative swing of the common source amplifier. So as VL swings in the negative direction, VDS decreases, and hence transistor is pushed towards the triode mode. Why? Because as VL increases in the negative direction, as VL decreases, or should I say, as VL swings in the negative direction, it increases in the negative direction. So as VL increases in the negative direction, the current through RL, it flows upwards, because VL is negative now and is increasing. So the current through RL, which is denoted by I subscript RL, it flows upwards with increasing magnitude. So as VL swings in the negative direction, the current through RL flows upwards with increasing magnitude and into the drain. But since VL is the AC component of the drain voltage, so as VL increases in the negative direction, VD increases in the negative direction, which means that the total voltage decreases, because total voltage is DC component plus AC component. So as AC component increases in the negative direction, total voltage at the drain will decrease, which will increase the drop across RD, which will increase the current through RD. So the current through RD is increasing, the current through RL is flowing into the drain with increasing magnitude, which means that the drain current will increase, because both of these currents, they will add into the drain current. So when drain current, and since drain current is equal to the source current increases. When source current increases, the voltage at the source will increase. So voltage at the drain is decreasing, voltage at the source is increasing, which means that VDS will decrease. So as VDS decreases, transistor is pushed towards triode mode, and hence VL will reach its maximum negative peak when transistor is at the boundary of triode and saturation mode. That is when VDS is equal to the overdrive voltage, VGS minus V threshold. VDS is VD minus VS, VGS is VG minus VS, VS gets cancelled on both sides, so we'll be left with VD on the left side and VG minus V threshold on the right side. VD is the sum of AC plus DC components, VG is the sum of, so VD is the sum of DC plus AC components, VG is the sum of DC plus AC components. I take VD to the other side, so capital VG minus capital VD, I replace it with VGD, and I replace the AC component of the drain voltage with, since the AC component of drain voltage is the load voltage, and under this condition, load voltage is denoted by VL maximum negative. So VD is replaced with VL maximum negative, and I take small VG to the other side, so it becomes minus VG. So VL maximum negative minus VG is given by this expression. So we have already, from the analysis of AC equivalent circuit, complete AC equivalent circuit, we have already related and expressed VL in terms of VI. So we can invert that expression and express VI in terms of VL. And we know that VI is equal to VG, because the voltage at the gate with respect to ground is the input voltage of the amplifier. So VG, we can express through the expression for the loaded gain, which relates VL with VI. We can express VI with VL and hence VG with VL. And under this condition, we replace VL with VL maximum negative. So when I put this term with VL maximum negative here into this equation and take VL maximum negative out common, this negative sign will make positive sign, and I'll be left with the factor of 1 plus this expression, which when taken to the other side will be inverted. So this is the expression for the maximum negative swing of common source amplifier, which can be approximated under this condition by this expression. So this is the approximate expression for maximum symmetric for maximum negative swing of common source amplifier. So having found out VL maximum positive and VL maximum negative, we can take the magnitude and then multiply the minimum of the two with the factor of 2 to find out the overall maximum symmetric swing of common source amplifier. So from the expressions of voltage gain, we see that voltage gain is inversely proportional to the source resistance. So if we want to increase the voltage gain, we must decrease source resistance. But we may not be able to decrease RS because RS may be constrained by the requirements on the bias point. So we may not be able to decrease RS to arbitrarily small values because of bias point constraints. So in that case, then the voltage gain is increased by dividing the source resistance RS into 2 and then connecting a capacitor CS in parallel with one of them. So what happens is that at AC, under the assumption that we are operating in the midband of the frequency range, this CS this CS has values of the same order as the coupling capacitor. So this CS will be short-circuited for the AC equivalent circuit at AC, which means that this node will be at AC ground, which means that the AC equivalent source resistance will be RS1, which is less than RS. So you can assume that we have divided RS previously into two resistors, RS1 plus RS2. So the total DC resistance, which is obtained by, because at DC this capacitor is open circuited, so the total resistance in the source branch at DC is RS1 plus RS2. So you can assume that RS1 plus RS2 is equal to RS as before, which means that you can use the same expressions for the DC, for the analysis of DC currents and voltages as I showed earlier. The only difference is that in those expressions, you need to replace RS with RS1 plus RS2. However, at AC, what happens is that, like I said, this capacitor will be short-circuited and the AC equivalent resistance in the source branch will be equal to RS1, which is smaller than RS. Hence, since the gain is inversely proportional to the AC source resistance, AC resistance in the source branch, and since the AC resistance in the source branch is now reduced, the gain will be increased. So this is the overall circuit for common source amplifier with partial source bypass. We have partially bypassed RS2. There is still some AC resistance RS1, but RS2 has been completely bypassed. So at AC, when we replace this with short circuit, this node will be shorted to ground and will be left with RS1. So this is what is meant by partial bypass. We have not completely bypassed the source resistance. There is still some left in the source branch. So this is the AC equivalent circuit of common source amplifier with partial source bypass. And this is the same circuit as we analyzed before. The only difference is that instead of RS, we have RS1. So in all of the expressions we derived earlier for input resistance, output resistance, voltage and current gain, and even the maximum positive and negative swings, in all of those expressions, you can simply replace RS with RS1 and you'll get the corresponding expressions for this circuit of common source amplifier with partial source bypass. So if RS1 is 0, or in other words, if I choose to connect the capacitor here directly at the source terminal, then at AC, this, because the capacitor will be connected here, this node will be directly connected to ground. So at AC, we'll have 0 resistance in the source branch. So the only difference between this circuit and the circuit we analyzed before is that RS is 0 in the AC expressions, not in the DC, in the AC, in the small signal, in the expressions for small signal parameters. So again, by simply replacing in those expressions for the small signal parameters, by simply replacing RS with 0, you can obtain the small signal parameters for the common source amplifier with full source bypass. And you can adapt the expressions of the maximum positive and maximum negative swing of the common source amplifier for this circuit as well. So maximum positive swing and maximum negative swing, if I go back to the circuit, So this is the circuit we have, right? So now we have RS1 and RS2, and RS2 is we have a capacitor at RS2. So the maximum symmetric swing, maximum positive swing does not depend upon RS, so there'll be no effect on maximum positive swing. However, maximum negative swing is given by this expression. So this RS is actually the RS in the AC equivalent circuit. So if you replace this RS with RS1, then you'll get the corresponding expression for maximum negative swing for partially bypassed amplifier. And if you replace this RS with 0, because this RS is now the RS in the AC equivalent circuit. So for fully bypassed circuit, the source resistance in the AC equivalent circuit is 0. So if you replace this RS with 0, then you will obtain the maximum negative swing for the corresponding maximum negative swing for the common source amplifier with full source bypass. You have to take care because you cannot just blindly put RS with 0 or RS1. You only need to put RS, you only need to modify the expressions which represent the AC expressions. That is, you can only modify the small signal expressions for the small signal parameters, such as the gain, current gain, voltage gain, input and output resistance. You cannot fiddle, you cannot modify the expressions for the DC currents and voltages, because the motivation to divide the source resistance into two was the fact that we did not want to change the DC source resistance because it may be set by the bias point. So a quick comparison between the common source amplifier with and without bypass capacitors. So I'm considering here a partially bypassed common source amplifier. Since RS1 is less than RS, there is no effect on the input resistance of the amplifier because RGS is infinity and RI is just R1 in parallel with R2. It is independent of RS. So the input resistance for the two amplifiers is the same. There is not much effect on the output resistance of the amplifier again, because the output resistance of the amplifier is approximated by RD. Voltage gain of the amplifier, open circuit and loaded with the bypass capacitor is definitely increased because the source resistance in the AC resistance in the source branch is reduced, as in the RS1 is less than RS, so the AC resistance in the source branch has been reduced, which increases the gain. Similarly, short circuit current gain and the loaded current gain will also increase because it also depends inversely on the source resistance, AC source resistance. If I can go back to the expression. So you see, it is inversely dependent on the resistance in the source branch in the AC equivalent circuit. So reducing the source resistance, the resistance in the source branch, the AC resistance in the source branch, we can increase not just the voltage gain, but also the current gain. So as an example, I have listed here, I've shown here, written down the small signal parameters and the corresponding expressions for the maximum positive and maximum negative swings for a fully bypassed configuration, for a fully bypassed common source amplifier configuration, under the assumption that small R0 is much, much larger. So input resistance and output resistance, they are independent of RS, especially under this assumption. So they are not affected by the bypass capacitor much. The voltage gain as well as the current gain increases. Positive swing remains the same. Negative swing is changed. We don't have RS anymore. RS has been replaced with 0 because for fully bypassed configuration, the AC resistance in the source branch is 0. So next is the common gate amplifier, and this is the complete circuit of a common gate amplifier configuration. As the name suggests, the gate terminal is common between the output and the input. So because of this capacitor CG, which is of the same order, as the coupling capacitor's gate terminal will be at AC ground and hence will be common between the input and output. So input is applied at the source through the coupling capacitor to avoid any interaction of the DC currents and voltages with the source signal, which is labeled VSIG, and RSIG models its internal resistance. And the output is taken from drain, which is again coupled capacitively with the load RL, because we don't want the DC component of the output to appear at the load. We want the load voltage to be an amplified version of the source segment, and we want to avoid the DC currents and voltages whose purpose is only to set up the bias point for the circuit. We want to avoid those voltages to appear at the output, from appearing at the output. So again, we will assume that VSIG is small enough that VGS satisfies a small signal approximation, and under which resulting amplifier will be a linear circuit. Hence, we'll carry out DC and AC analysis separately, and we can later on combine the results of the two analyses through the principle of superposition. So this is the DC equivalent circuit for a common gate amplifier, which is obtained by open circuiting the capacitors and by short circuiting the source to ground. So AC source to ground. So as you can see, it is the same voltage divider biasing network with source regeneration resistance. So you'll find the gate voltage as before, and then you will analyze the gate voltage and see if the transistor is in on state or not. If it is, then assuming that the transistor is in saturation, you'll find the bias point, the output drain current and drain to source voltage. Again, for simplicity, I have ignored the channel length modulation here, and you will analyze VDS or VD. And if it comes out to be VDS comes out to be greater than VDS minus V threshold, or if VD comes out to be greater than VG minus V threshold, then this is indeed the bias point. The transistor is indeed in saturation. Otherwise, the transistor is in triode mode, and you'll have to use the triode mode equation to find the drain current and the drain to source voltage. So we will solve these two equations to find the bias point. However, please note that if the bias point is given by these two equations, then the transistor won't be in saturation mode, which means that we won't have any amplification. So in order to bias the circuit, we'll have to make sure that the bias point is set by these equations. The circuit is designed so that the bias point satisfies these equations. So this is the complete small signal AC equivalent circuit for the common gate amplifier, in which I have replaced the transistor with the small signal T model. So we analyze the common source amplifier by replacing the transistor with small signal hybrid pi model. This time we replace it with small signal T model. And the resistance seen looking into the input of the amplifier, which is made up of these two terminals, this node and ground. So this is the input port. This node and ground makes the output port. So the resistance seen looking into the input port is Ri. The resistance seen looking into the output port is R0. Voltage at the input port is Vi, and the current entering the input port is I6. So this model is obtained. This circuit is obtained by killing all the DC voltage sources and by replacing the coupling as well as the gate capacitor with short circuits. So doing so brings the gate at AC ground. So this circuit is this configuration is not unilateral. Because of this resistance R0, small R0, you can see that there is a path from the output back to the input. So any change in the output voltage will affect the input. For example, if VD changes, then the current through R0 will change, which will change the source current IS, which will change the input voltage VI. So the changes in the output voltage will affect the changes on the input side. So this is not a unilateral amplifier configuration, which is why the input resistance should be computed without any constraint of open circuiting the output. So we keep the load in the circuit, and we compute the input resistance Ri. So Ri by definition is given by the voltage at the input port divided by the current entering the input port, which is I6. So Vi over I6 is Ri, and we can represent it in this way, because if we look at Ri, then Ri is Rs in parallel with the resistance seen looking to the right into this circuit between this node and ground. So whatever is the resistance seen looking towards the right into this circuit between this node and ground, that resistance in parallel with RS gives us Ri. So that resistance is the voltage between this node and ground divided by the current entering this node. Since the current leaving this node is Is, the current entering this node will be minus Is. And the voltage between this node and ground will be minus VGS, because the voltage between this node, which is ground, and this node is VGS. So the voltage between this node and ground will be minus VGS. So this resistance, the resistance seen looking towards the right between this node and ground, this resistance is given by the ratio of minus VGS to minus IS, which is equal to VGS over IS, and IS is equal to ID, so it is equal to VGS over ID. So VGS over ID in parallel with RS will give us the input resistance, Ri. So ID is the sum of two currents, GM VGS. So ID is this current, which is equal to GM VGS plus IR naught. IR naught is the current through R naught. So it is the sum of the two currents, where IR naught is the current flowing through R naught, and it is given by this relation. So IR naught can be found by dividing the voltage across R naught with R naught. So the voltage across R naught is VD minus this voltage, which is VI. Voltage at this node with respect to ground is VI. Voltage at this node with respect to ground is VD. So the voltage difference between this node and this node is VD minus VI over R naught will give us IR naught. VD is minus ID times RD in parallel with RL. So VD is minus ID times RD in parallel with RL, and VI is VGS over R. Minus VI is actually plus VGS. You can see it from this circuit here, that the voltage at this node with respect to ground, which is VI, is equal to the negative of voltage of this node with respect to ground, because the voltage of this node, which is ground, with respect to this node is VGS. So voltage of this node with respect to ground is minus VGS, which is equal to VI. So VI minus VI is equal to minus VGS, and minus VI is equal to VGS. So we can write ID in terms of GM VGS and IR naught again. Take the terms with IR naught onto the other side, simplify, and we get IR naught in terms of VGS through this factor. So we replace in this expression, we replace IR naught with this factor. We take VGS out common and simplify to get this factor. So VGS over ID is inverse of this factor, which is given by this term. So this factor in parallel with RS gives us the input resistance of common gate amplifier. So under this useful assumption that small r naught is much greater than capital RD in parallel with capital RL, the numerator can be approximated with small r naught, and we can assume, since small r naught is very large, we can assume GM small r naught to be much greater than 1. So the denominator will be approximately GM times small r naught. R naught will get cancelled out, and the input resistance will be approximated by this more commonly found expression of RS in parallel with 1 over GM. So this is the approximate and more commonly found expression for the input resistance of common gate amplifier. Output resistance is found in a similar manner. So if I go back to the complete AC equivalent circuit of common gate amplifier, then output resistance R naught is RD in parallel with the resistance seen looking into the drain between this node and ground. So resistance seen looking into the circuit towards the left between this node and ground, whatever that resistance is, its parallel combination with RD will give us R naught. So R naught is found by short circuiting VI. So we short circuit the output, the input of the amplifier. So we connect this node, this source node, directly to ground. So when this node is directly connected to ground, then RS and this circuit is essentially shorted out. So source terminal is directly at AC ground. So the resistance seen looking into this side towards the left of the circuit between this node and ground is found by connecting a current source between this node and ground, and then measuring its terminal voltage. So R naught, capital R naught, the output resistance, like I said, is given by RD in parallel with Vs over Is, where Vs is the terminal voltage of the current source which is applied between the drain node and ground towards the left of RD. So this is the reduced AC equivalent circuit when we short circuit VI or the input of the amplifier to ground. So this is the source terminal which is directly shorted to ground. So in this circuit, if we look closely, then this source terminal and this gate terminal, they are both grounded. So VGS is 0. So when VGS is 0, then this current is 0. So this branch is open circuit. So this current source only sees R naught. So Vs over R naught, small R naught is Vs over Is is equal to small R naught, because this current source only sees this resistance small R naught. So the output resistance of the amplifier is given by RD in parallel with small R naught. On the other hand, if the short circuit Vsig instead of Vi, if we short circuit this node to ground, then we'll have Rsig in parallel with Rs connected at the source, between source and ground. So now the source terminal is not grounded anymore. It has a resistance Rsig in parallel with Rs. Rsig in parallel with Rs is connected between source and ground. So R out, which is the output resistance measured by short circuiting Vsig, is given by RD in parallel with the resistance of this circuit, which is the reduced equivalent circuit towards the left of RD, looking into the circuit. And this resistance is again found by connecting a current source between drain and ground, and then measuring its terminal voltage. So we can redraw this circuit in a way which makes it easier to analyze. So I have connected this end, because this end of the current source is directly grounded, so I've connected it directly to ground, and this end of R naught is connected to this mutual end of these two resistors. So it is connected to this end of R naught is connected to the common terminal of these two resistors, and the other two terminals of these two resistors, they are grounded. So this is actually the same circuit as this one. It just makes it easier to analyze. This circuit looks easier to analyze. So we just need to express IS in terms of Vs. So IS is equal to this current plus this current. This current is GMVs. This current is this voltage here at this node with respect to ground, which is Vs, divided by the total resistance, which is small R naught plus this parallel combination. So GMVGS plus Vs over small R naught plus this parallel combination. This gives us IS. Now VGS, which is the voltage of ground with respect to this node, is actually the negative of the voltage of this node with respect to ground. So the voltage at this node with respect to ground can be found by the voltage division rule, because R naught and this resistance, this parallel combination, is in series. So Vs, which is the voltage at this node with respect to ground, divides between small R naught and the voltage at this node. So the voltage at this node is this parallel combination divided by this parallel combination plus small R naught times Vs. And negative of this voltage is VGS. So Vs times the parallel combination divided by parallel combination plus small R naught is the voltage at this node with respect to ground, and VGS is just negative of this voltage. So we have Vs common in both terms. We take Vs out common, we simplify, and then the ratio of Vs to Is is equal to the inverse of this factor, which is given by this expression. So R out, which is the resistance, output resistance of the amplifier, plus the small signal source, is given by RD in parallel with this factor. Again, we can make use of this useful approximation that small R naught is much greater than RD, which makes it much greater than this parallel combination, because this parallel combination is much smaller than RD because of 1 over GM, and Rsig is also 1 over GM is a small resistance, and Rsig is typically also small. So this parallel combination is much smaller than RD. So if small R naught is greater than RD, then small R naught is much greater than, definitely much greater than this combination. So the numerator is approximately small R naught. In the denominator, we have, since this factor is smaller, this parallel combination is smaller than 1 over GM, this product is less than 1, and this denominator is less than 1. So this factor is even greater than R naught, small R naught. which means that R out is very well approximated by RD. Similarly, since capital R naught is RD in parallel with small r naught, and small r naught has been assumed to be much greater than capital RD, so capital R naught, which is the output resistance of the amplifier alone, is also very well approximated by capital RD. So these are the useful expressions, more commonly found expressions for the output resistance of common gate amplifier under the useful assumptions. This is the AC equivalent circuit for computing the open circuit voltage gain of the amplifier, in which I have open circuited the output. So I have disconnected the load and I call the output voltage as V. I designate the output voltage with V naught. So V naught is minus ID times RD, and ID is the sum of these two currents, GS plus IR naught. So V naught is minus ID RD, and ID is the sum of these two currents. We've already found IR naught previously for the complete AC equivalent circuit in which we had RL. So in that expression, if we simply replace RL with infinity, we'll get the expression for IR naught for this circuit, because open circuiting, the output is equivalent to replacing RL with infinity. So replacing RL with infinity in 39, which gives the expression for IR naught for the complete AC equivalent circuit. So replacing RL with infinity in that expression, we get this reduced expression for IR naught, which when put back here gives us V naught in terms of VGS. Because VGS is common, we can take it out. We can take it outside and then simplify. And since VGS is equal to minus VI, or VI is equal to minus VGS, we get V naught in terms of VI. So this factor here, which is V naught over VI, gives us the open circuit voltage gain of common gate amplifier. The overall voltage gain is obtained by finding the load voltage, and the load voltage VL can be obtained from this expression by simply replacing RD with RD in parallel with RL. Because if in this circuit we put RL back in, then the total AC resistance at the drain, between drain and ground, becomes RD in parallel with RL. So we'll write VL as minus ID times RD in parallel with RL, and then we'll use the full expression for IR naught, which is equivalent to putting RD or replacing RD in this expression with RD in parallel with RL. So VL is obtained, is given by a similar expression. In fact, with this expression, VL is given by this expression by replacing RD in parallel, RD with RD in parallel with RL. So we replace RD with RD in parallel with RL. Just like using this expression, replace RD with RD in parallel with RL. So this is VL in terms of VI, and VL over VI times VI over VSIG gives us VL over VSIG, which is the overall loaded voltage gain of common gate amplifier. So VL over VI is this factor, and VI over VSIG is the input, is the loading factor on the input side. So VI is RI over RI plus RSIG times VSIG. So VI over VSIG is this factor. So the product of this factor and this factor gives us the overall voltage gain of common gate amplifier. So again, using this useful assumption that small r naught is much greater than RD, we can approximate the input resistance and output resistance like this, because in approximating the input resistance, we assume that small r naught was much greater than RD in parallel with RL. So if this is true, then small r naught is definitely much greater than RD in parallel with RL, because RD in parallel with RL is smaller than RD. So this assumption enables us to use this approximation. Furthermore, we assumed this to approximate the output resistance with RD as well. So with this assumption, we can approximate the input and output resistance like this, and then we can approximate the open circuit voltage gain with GMRD, because small r naught is much greater than RD. So the denominator is approximated by small r naught. Since small r naught is large, GM r naught is much larger than 1. So then we approximate the numerator by GM r naught. So r naught gets cancelled and we're left with GMRD. So GMRD is the approximate expression for the voltage gain, open circuit voltage gain of common gate amplifier. Similarly, small R naught is much greater than RD, means small R naught is much greater than RD in parallel with RL. So the denominator is approximated by small R naught, numerator is approximated by GM R naught gets cancelled out. So we'll be left with GM times RD in parallel with RL times this factor. So we get GM times RD in parallel with RL times this factor, in which we have replaced RI with this approximation. So if we open this product, then RD in parallel with RL is RD RL over RD plus RL. So we can separate out RD and the other factor RL over RD plus RL. So GM RD is AB naught, and the other factor can be written separately, RL over RD plus RL. Since RD is R naught, so we replace RD with the output resistance. So this factor is actually equal to the product of these three terms. The loading on the input side, open circuit voltage gain, and loading on the output side. So if you look closely, then this is the expression one would obtain if one solved the this unilateral model of two-port voltage amplifier. So in this unilateral model, if I connect the load resistance here, then VL will be AV naught times RL over RL plus R naught. So I have this factor times AV naught times VI, and VI is RI over RI plus R sig times V sig. So I'll have this factor times V sig. So V sig can be taken on to the other side. VL over V sig will give me AV, and you'll see that from this circuit of unilateral model of two-port voltage amplifier, I get this expression for the voltage gain VL over V sig. So under these assumptions, the approximate voltage gain, open circuit voltage gain, and the approximate overall voltage gain, they are given by these more commonly found expressions, in which this expression for the overall voltage gain, it follows from the analysis of unilateral model of two-port voltage amplifier. The short circuit current gain of common gate amplifier can be found using this AC equivalent circuit, in which I've replaced the output RL with 0. So I've short circuited the output. In other words, I've replaced RL with 0. So since RD is in parallel with the short circuit, it's ineffective, and I've chosen not to show it. So the current flowing through short circuit, output short circuit, is I subscript O comma S, and it is equal to the negative of the drain current. The drain current flows into the drain, which is given by the sum of these two currents. So IOS is minus ID, and ID is GM VGS plus IR naught. We've already found the expression for IR naught in 39. So in that expression, if we replace RL with 0, we'll get the expression for IR naught for this circuit, which is VGS over R naught. And actually, you can verify it very easily. Because this node is grounded, this node is the same as this node. So the voltage at this node with respect to the voltage at this node with respect to this node is the same as voltage at this node with respect to this node, because these two nodes, they are at the same potential ground. So this voltage of this node with respect to this node is VGS. So voltage at this node with respect to this node is VGS. So IR naught is VGS over R naught. So putting this expression for IR naught back in this equation, and taking VGS out common, and realizing that minus VGS is equal to VI, we can express IOS in terms of VI through this factor. VI is given by definition, is given by I sig, which is the input current, times RI. So VI is I sig times RI. RI, we have already found the expression for RI. In that expression, we can replace RL with 0, because in this circuit, RL is 0. So if we replace RL with 0 in that expression, we'll get this reduced expression for RI. And dividing with I sig on the other side will give us the short circuit current gain in terms of the product of these two factors. The overall current gain is obtained by finding the load current. So if we look at the complete AC equivalent circuit of common gate amplifier, then the load current is given by the division of minus ID into RD and RL. So IL is given by minus ID times RD over RD plus RL, which is the current division of minus ID. So IL is minus ID into RD over RD plus RL. ID is again GM VGS plus IR naught. We've already found IR naught, so we use the full expression this time, because we have connected the load back in. No need to use special values for RL. So take VGS out common, simplify, and replace minus VGS with GI and GI with I sig times RI. So after simplification, we get this result for IL. So IL over I sig is given by this factor then, in which Ri is Rs in parallel with this combination. So this is the full expression now. And then multiplying this Ri with this term and this term will give us IL over I sig, which is the overall loaded current gain of common gate amplifier. Again, under this assumption that small r naught being much greater than Rd implies that small r naught is much greater than this parallel combination. And since small r naught is very large, we can assume that GM r naught is much greater than 1. Furthermore, we can make this very reasonable assumption that 1 over GM is much smaller than Rs. This is very reasonable as well. So using these assumptions, we can approximate these two expressions in 59 and 61. So if GM R naught is much greater than 1, the numerator here is GM R naught, and R naught gets cancelled out. So we'll get GM here. And same for this. GM R naught is much greater than 1, so denominator is approximated by GM R naught gets cancelled, we'll get 1 over GM here. And since we have assumed 1 over GM is much smaller than RS, so this parallel combination is approximately 1 over GM. Times GM gives us 1. So the short circuit current gain of common gate amplifier is almost unity. And then using the same assumptions, small r naught being much greater than this parallel combination means the denominator is approximated by small r naught, numerator is approximated by GM R naught gets cancelled, and this factor becomes GM. And this factor again becomes in the denominator, the denominator is approximated by GM R naught, numerator is approximated by small r naught gets cancelled, we get 1 over GM, and 1 over GM in parallel with RS is approximately 1 over GM, because 1 over GM is much smaller than RS. So this factor becomes 1 over GM, this factor is GM, GM gets cancelled with GM in the denominator and will be left with this factor. So the loaded current gain of common gate amplifier is just given by this factor at the output. So you can see that in this expression in 61 and in 59, this is the expression for loaded current gain, this is the expression for short circuit current gain, this is the expression for overall voltage gain, and this is the expression for open circuit voltage gain of common gate amplifier. So in all of these expressions, there is no negative sign, which indicates that common gate configuration is a non-inverting amplifier. So the maximum symmetric swing of common gate amplifier can be obtained by finding the maximum positive and negative swing. So we analyze the overall complete circuit of common gate amplifier, in which due to the output capacitor, the voltage across the load, total voltage across the load is just AC. The total voltage across the load has just AC component. So it is written as V subscript small n. The DC component is blocked by the capacitor. And since the output is connected to the drain, so the output voltage is just the AC component of the drain voltage. The DC component is blocked by the capacitor. So the output voltage VL is small Vd. So during the positive half cycle, as VL increases, the current through RL increases. And the drain voltage also increases, because when VL increases, then AC component of the drain voltage increases, which decrease. So when drain voltage increases, the drop across RD decreases, which decreases the current through RD. So as VL swings in the positive direction, the current through RL is increasing, the current through RD is decreasing. Since the drain current is given by the current through RD minus the current through RL, drain current decreases. And VL achieves its maximum positive value when the drain current becomes 0. That is when the transistor enters cutoff mode. So under this condition, the current through RD, which is given by VDD minus total drain voltage over RD, becomes equal to the current through RL, which is VL over RL. And under this condition, we replace VL with VL maximum positive. We denote VL with VL maximum positive. So VL maximum positive is VL under this condition. So V has DC component, capital VD, and AC component, which is equal to the load voltage So we take it to the other side. So this is the contribution due to the AC component of the drain voltage. AC component of drain voltage is the load voltage, and under this condition we denote it by VL maximum positive. So we take it to the other side, it becomes positive, and we realize that this term is the DC drain current. So at DC, when there is no capacitor, the current through RD is the same as the current as the drain current. So current through RD VDD minus DC voltage VD over RD. So this is the current through RD at DC, which is the drain current, DC component of the drain current. So 1 over RL plus 1 over RD, when taken to the other side, the inverse of 1 over RL plus 1 over RD becomes RD in parallel with RL. So the maximum positive swing of common gate amplifier is given by this expression, which is the same expression as we obtained for common source amplifier. And you should expect it because the output is taken from the drain. And hence, we get the same maximum positive swing for the common gate amplifier as we did for the same swing as we did for the common source amplifier. So this is the maximum positive swing for common gate amplifier. It depends upon ID, the DC component of drain current, the drain resistance, and the load resistance. On the other hand, if VL swings in the negative direction, as VL increases in the negative direction, the current through RL flows upwards because now VL is negative. So the current through RL flows upwards. So as VL increases in the negative direction, the current through RL increases. The current through RL flows upwards with increasing magnitude. So it flows into the drain terminal. And since VL is increasing in the negative direction, the AC component of drain voltage is increasing in the negative direction, which means that the total drain voltage is decreasing, which increases the drop across RD, which increases the current through RD. So the current through RD is increasing. The current through RL flowing in the upwards direction into the drain is increasing. So the drain current increases, which increases the source current. So increase in source current increases the source voltage. So drain voltage is decreasing, source voltage is increasing, which means that VDS is decreasing. So as VL swings in the negative direction, VDS decreases and transistor is pushed towards the triode mode. So VL attains its maximum negative value when transistor enters the triode mode. That is when VDS equals the overdrive voltage. So VDS is VD minus VS, VGS is VG minus VS, VS gets cancelled out, we'll get VD equal to VG minus V threshold. VD has DC and AC components, VG has DC and AC components. AC component of VD is VL, which under this condition is denoted by VL maximum negative. We take the small VG, which is the AC component of VG of the gate voltage, to the other side, so it becomes minus VG. We take capital VD to the other side, and capital VG minus capital VD is denoted as VGD, and then we have this as the minus V threshold voltage. So VG in this case is 0 because the gate is at AC ground and AC voltage at the ground is then 0, which gives the maximum negative swing of the common gate amplifier to be equal to VGD minus V threshold. So VGD is the DC voltage at gate minus the DC voltage at drain. So having found out VL maximum positive and VL maximum negative, we find the magnitude of the two, and whichever of the two magnitudes is smaller, we multiply that with 2 to get the overall maximum symmetric swing for the common gate amplifier. So this brings us to the end of this lecture. Thank you very much for your time. I will see you in the next class. Take care.